I think it's recording now. Is it recording? It looks like it is recording. All right, it's recording. Good. All right. So, let's see. Where are we now? I'm not sure if you've all watched the last video, but we were getting into. We're kind of in this little series of computational tools that we're discussing, and all, sort of basic chemical informatics, right? So using computer tools to make our chemistry lives easier and maybe eliminate the need for doing tons of experiments. So I think what we did earlier in the synchronous lecture last time is we started talking about these physicochemical properties, C log P, polar surface area, things like that, and the Lipinski rule of 5 and the Weber rules, which are kind of rules we use for drug likeness. Like, is a molecule drug-like? Does it have any potential to be an orally bioavailable drug, right? Okay, and we also remember metabolism, right? If we're going to get into metabolism again, and I know it's been a little while ago, I'm not going to review all of metabolism, but maybe I'll just show a little bit from that PowerPoint, the metabolism PowerPoint. Oops. Okay. The main things, I guess, for now are remember what phase 1 and phase 2 metabolism were. What were phase 1? Anybody have any examples of phase 1 and phase 2 metabolism? Or yeah, I mean, just generally speaking, a drug. What does a phase 1 reaction do versus phase 2? Well, as you can see in the outline, oxidation, reduction, and hydrolysis were big phase 1 things. So changing of a functional group, or oxidizing a carbon, oxidizing a nitrogen, things like that. Reduction can happen also, reduction of a reducible functional group. Hydrolysis with soluble enzymes. What was phase 2? Anybody remember what's the general idea of phase 2? So generally speaking, phase 2 was conjugation, like attaching another molecule to your drug, right? And that would enhance solubility and excretion through the kidneys, right? Let me see if I can show a couple of these things real quickly. Like, I would say the biggest one, for phase 1, phase 1, oxidation of carbon. A big one for phase 1 was like oxidative dealkylation. Let's just show that real quick. These ones are a big deal for drug metabolism. So it's like cleavage of a alkyl group off an amine or something like that. So you'd oxidize the carbon to a hydroxy group, and then it would cleave. Those kind of things. That's like classic phase 1 metabolism. Phase 2 metabolism was when we attached a conjugate like glutamic acid or glucuronic acid. Let's just show that real quickly to review it, what phase 2 metabolism was, right? Let's go down there, phase 1, blah, 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 phase 1, blah, blah, blah. So we did this, but we just want to make sure we understand the rough idea of phase 1 and phase 2. Okay, blah, blah, blah. Let's go to phase 2. Hydrolysis. Okay, so phase 2 was this conjugation business where we basically take a reactive functional group and we attach something to it. A big common one is glucuronic acid, right? Glucuronic acid, sugar with a bunch of hydroxy groups, and that really aids in excretion. Sulfate's a big one. Glycine, glutamine, like just amino acids even, will enhance solubility and excretion. Also, glutathione was the one that attacked electrophiles. Methylation actually can occur in acetylation. Okay, so let's go back to where we were in the other lecture. Okay. Oh yeah, one more thing. Sorry. Where's my? Sorry. Okay, where are we? Okay, so does I imagine now you guys have watched the last PowerPoint where we talked about smiles, right? What was smiles? Anybody have a 2-second explanation of what smiles is? Smiles, method to represent chemical structures, right? So that's a big deal because we need that. We're going to be using it in a second. It was a kind of a computer language to describe the chemical structure of molecules, right? So, and we can use that to generate 2D and 3D structures. That's what we did in the asynchronous lecture. Okay, so given smiles, now we're going to predict drug likeness using those Lipinski rules and the Weber rules. And we're going to use computer tools to let us do that, okay? All right, so let's try that. So drug likeness, you know, this is a very common thing, especially in high throughput screening of drugs. We're going to use this mole inspiration molecular properties tool to do this. Okay, and we're going to demonstrate drug likeness for a couple classes of molecules. All right, let's see if we can do this. First, orally available pharmaceuticals, which should be drug-like, right? It's a good test subject case, right? So, and then we'll also do some preclinical pharmaceutical candidates. Then we talked about this neuropeptide Y1 antagonist. It was discussed earlier when we were talking about drug likeness. So we'll take a look at that also. All right, and you know, preclinical probably means that it's not a perfect drug. Often, preclinical means you're trying to optimize potency, but don't really care about oral bioavailability. Okay, and then also like a peptide, and we know peptides are good or bad drugs orally. Usually pretty bad. Okay, so this will be a prediction. We can predict that that's going to be a bad, undrug-like molecule. Okay, here we go. So known oral pharmaceuticals. Oh yeah, and remember these are the rules for drug likeness that we talked about earlier. The Lipinski rule of 5 and the Weber rule of 2, I guess. Remember with the Lipinski rule of 5, you have these rules, and but one violation is allowed. So if you have one violation, it's still Lipinski compliant. With Weber, no violations are allowed. All right. Okay. So what are the rules again? Hydrogen bond donors less than or equal to 5. Hydrogen bond acceptors. So that's like just oxygen, things like lone pairs usually. And the, less than or equal to 10. Molecular weights less than 500, and C log P, the prediction of aqueous solubility, is less than or equal to 5. And for Weber, it's rotatable bonds are less than 10, and less than or equal to 10. Polar surface area is less than or equal to 140. Okay, so let's take a look at warfarin. So this was the anti-blood clotting drug. I give a smiles string right there. Of course, if you needed to look up smiles, you could probably check PubChem or something. That's where we like to look up these smiles strings. The nice thing is I can easily basically copy this structure via the smiles string. Okay, so let's go get that. I'm going to copy it on my clipboard. Copy it on my clipboard. Now we're going to go over to this website, this mole inspiration thing. So if I Google mole inspiration, it comes right up, yeah. And it's a really nice free set of tools. And one of the things I can do is calculate molecular properties and bioactivity. We're not going to try to predict bioactivity. I mean, if it's a very known drug, it and how it inhibits blood clotting is pretty well characterized. I think it's the B core protein. Okay, so molecular properties, we'll go in here. And I can just paste in that SMILES string that I got. Oops, uh-oh. There it is. Okay, so I pasted in that's the warfarin SMILES string. And we're gonna predict the properties. And this is an orally available drug, right? So it's predicted to have good drug likeness. And let's see if it all matches now. Okay, so here we have warfarin. Remember, mi log p is just a version of c log p. 3.03, is it compliant or not? Well, if the rule is less than or equal to 5, then yes, definitely compliant. Polar surface area is actually used in the Weber criteria, and yeah, it looks like it's compliant. Number of atoms is irrelevant. The molecular weight, though, 300. Yep, that's good, less than 500. NOH, or sorry, NON is the hydrogen bond acceptors. There's 4 of them. Okay, good, we're in compliance. These are the donors. There's 1. Okay, that is in compliance. And then it basically tells you there's no violations. Rotatable bonds is is 4, which is definitely less than or equal to 10. And yeah, we basically say this is a drug-like molecule, which is nice, and it matches what we know about warfarin. Okay. Any questions about that? Okay, it is a orally bioavailable drug. You know, you take it, and 100% of it is basically transmitted to your bloodstream. So it's a high orally available drug. This is one of the sulfa drugs, antibiotic, and I think it has a slightly lower oral availability. Let's see. Let's do the same analysis. So I'm going to get that SMILES string. Calculate properties. Okay, there it is. And does it match the rules? So C log P is very small now. Does that suggest it's greasy or aqueous? Remember what the relative meaning of C log P was? Big numbers of C log P were like kind of greasy molecules. This is a fairly aqueous soluble molecule, highly soluble, right? All these oxygens and nitrogens and sulfur and everything, all of those kind of enhance the aqueous solubility of it. Okay, polar surface area 98, so that matches the Weber criteria. Atom count doesn't matter. Molecular weight is less than 500, good. Hydrogen bond acceptors is 6, which matches Lipinski. Hydrogen bond donors is 3, which matches Lipinski. It suggests no violations. Rotatable bonds 3, so everything's cool, and that also makes sense for this orally available drug. Okay, so this is consistent with an oral pharmaceutical, orally available pharmaceutical. Okay, Lipitor. So Lipitor is actually, it's used as a cholesterol lowering medication, but its availability is actually kind of low. Let's see why. Maybe you can make a prediction that maybe something is going to be, out of compliance. So let me get that SMILES string. Oops. Okay, so this somewhat orally non-bioavailable drug, it's got some problems according to Lipinski. So C log P is a little higher than 5, so that's technically a violation. Polar surface area is okay. Atom count, molecular weight's a little high, and it, for a drug that is actually kind of a large drug with a lot of these benzenes and everything like that. So that's not too surprising. Hydrogen bond acceptors 7 and donors are 4, so that's in compliance. But it was two violations. Technically, not a drug-like molecule, and with a low oral bioavailability, that kind of makes sense. Also, rotatable bonds is greater than 10, so that also makes it in violation of the Weber rules. Now, I mean, it has oral availability problems, but it can still be used as a drug. It's just the dose has to be a little higher, accepting the fact that it's not all going to be absorbed, right? Okay. So let's see some more drugs. So we talked about this neuropeptide Y and Y1 receptor antagonist thing, and we were talking about, when did we bring it up? It was during our discussion of drug likeness. Let's go use these tools to analyze it. And remember, if you look back in that maybe 1 or 2 PowerPoints ago, or 1 or 2 lectures ago, this was the compound. It was sort of poorly potent, 2 micromolar, not super good, but it's very good at bioavailability. So let's see if the bioavailability, oral bioavailability matches what they found. So I'm slowly getting a new homework, and I'm still a little behind on grading, but the next homework you will be using some of these tools, so it'll be a nice experience for you guys. All right. Okay, so let's take a look. Whoa, did that work? Yeah, there it is. Okay, so that's that lead structure, and let's see. I mean, it's kind of jumps to the chase and says there's 1 violation. Of course, that's probably due to the C log P being greater than 5, right? My log P, C log P greater than 5. TPSA is okay. Atom count, molecular weight's okay. Acceptors is okay. There's no hydrogen bond donors. But yeah. I mean, it actually seems like a reasonably orally bioactive drug. Kind of validates the Lipinski rules a bit, right? Yeah. Okay. So, and then they did this optimization campaign where they added some stuff. They added a piperidine up here. They added a couple carbons, another piperidine down here. But when you start adding lots of structure, I mean, that's going to kind of hurt the drug likability. It certainly adds a lot to the molecular weight, and it doesn't get absorbed as well. So yes, the IC50 is now 1 nanomolar, very nice, right? But they're a very bad availability. And this is a very common problem people experience in medchem. So where's the smiles? That's a big smiles string. I'm going to copy that and paste it in and see if we can identify what the problem is. So I got the smiles. Paste it. Properties. Okay, let's see. Actually, so let's see. All right, we got C log P is much higher now. So it's kind of a greasier molecule. And that's probably because of all these extra ring systems. So that's in violation. TPSA is acceptable. Atom count's good. And the molecular weight is too high. So that's two violations. These 2 are fine. Rotatable bonds is at 11, so actually Weber says it's going to be bad also. So yeah, it just shows these rules seem to have some experimental validation. All right, good. Let's see what else I have here. So yeah, these tools are nice. They can quickly determine things like these properties. We can also do it kind of manually, but having a tool do it for you is really cool. Okay, what about peptide-like pharmaceuticals? So let's talk about vancomycin. Vancomycin, of course, is a very crazy. Is that vancomycin there? I think that's is that vancomycin? Let me check on that real quick. 1 second. So that's not vancomycin. I think this structure here is the bottom molecule. So vancomycin is a crazy antibiotic, sort of for like kind of last stage bacteria that's drug resistant to everything. So that's the structure of vancomycin. And you can probably make a guess that it's not going to be orally bioavailable based on the crazy structure, a lot of polar functional groups, and huge molecular weight. So it's probably not going to be very orally available, and it's not. It's not. It's used intravenous, and the bioavailability is 5. So it's actually, I mean, this slightly absorbed, surprisingly, actually. But let's take a look at the drug likeness parameters of it. Copy the smiles. Properties. Okay. So there we go. Let's take a look, see here. So C log P is very, I mean, it's very aqueous soluble, as you'd imagine, with all these nitrogens and, you know, alcohols and phenols and the sugar type thing. So it's a very aqueous soluble. That's actually not in violation. Oops, sorry, what's going on here? 1 second. Polar surface area is out the roof, right? 530. Very polar molecule, and that definitely violates the Weber rules. Number of atoms, whatever, but the molecular weight's huge. The number of hydrogen bond donor or acceptors is 33 as opposed to 5, and the hydrogen bond donors are 21 acceptors as opposed to 10, donors as opposed to 5. There's 3 Lipinski violations, and also the rotatable bond count's too high. So yeah, you know, it's generally speaking, peptides are poor pharmaceuticals, and so we're going to make that same kind of guess for this other molecule. I don't know why this is doing this. 1 sec, sorry. I'm seeing some weird stuff on my screen. All right, there we go. So this is another peptide drug, and I think this is also an antibiotic. Let's take a look at it. It also has this sort of general macrocyclic structure with various amino acids and sugars and stuff. Nice structurally complicated molecule. This is a drug that's administered by IV, as expected for peptides like this. So let me get that one. I love how, I mean, smiles, and not only does it encode this crazy chemical structure in a series of letters, but it also, all these little bracketed things are the stereochemistry. So it shows it encodes the stereochemistry of all these atoms. Every stereocenter is encoded in this series of letters. So smiles is a cool thing. Okay. All right, so for this oritivancin, face of smiles. Okay, so it actually has a much higher C log P than vancomycin. Vancomycin's roughly around 1. I mean, this is at 5, so it's a little greasier. Why is it so greasy? Any guesses? Looking at the structure, what makes it greasy? Well, like these benzenes and the the chlorobenzene, etc. Those things will enhance the greasiness of it and boost the C log P. TPSAs also out the roof, much greater than 140. Atom count, molecular weight is huge. Hydrogen bond acceptors 36 versus 10. Donors 22 versus 5. 3 violations of Lipinski. Rotatable bonds 19. So definitely in violation of both those things. So yes, I mean this is consistent with what we'd expect. All right, good. Let's talk about, let's use computer tools to predict metabolism now, okay? So this is different than drug likeness. And there's nice computer tools that we can actually make a prediction on phase 1 and phase 2 drug metabolism, right? And phase 1 was simply transformations, maybe an oxidation at a certain atom, usually oxidations on a carbon or maybe a nitrogen or something like that. Okay, so let's see. And then phase 2 was attachment of conjugates, right? So there's some cool computer servers that seem to be working. There's one of them's a little problematic. We'll see. One's called the Nerd server, new resources for drug discovery. This is a collaboration between the University of Hamburg, one of the universities in Prague, and also a university in Milano. And there's also something called the Biotransformer server. This seems to be better for phase 2 drug metabolism prediction. This is a project of the Metabolomics Innovation Center. It's a thing in Canada. It's been a little funny, so we'll see if it works for me. We're going to give it a shot. Okay, so prediction of metabolism. Let's see. So we're going to do the Nerd server first, which is mostly useful for phase 1 metabolism. All right, so I'm going to Google that site in a second. And we're going to demonstrate 3 tools on the Nerd server that provide complementary information. One is a tool called FAME3, which determines the sites and maybe statistical probability of phase 1 metabolism. So just like look at a molecule, figure out where in the molecule is likely to be metabolized by phase 1. Because you can change the structure to maybe avoid metabolism, right? And there's also the FAME3, which offers the sites of phase 2 metabolism. So which atoms might get conjugated. So it uses some pretty sophisticated algorithms to do this. And then it also has a tool called Glory, which is it actually tries to predict the structure of the metabolites, right? That's kind of cool. You can actually see what you might expect in metabolism, and for that why is that useful? Because if you do an experiment, like if you're actually studying a drug, you can actually look for these metabolites and use HPLC or mass spec or something to actually identify them, and then maybe try to avoid metabolism. Because often metabolism is something you want to avoid. You don't want your drug to get metabolized easily. Okay, so let's go to the Nerd. We're going to go to the Nerd server for phase 1 metabolism. Okay, so let me go back. Let's get that link real quick. Okay, all right, so I'm going to open up that link real quick. Okay, so paste it. It comes up, it gets redirected. There's no problem. The link changed a little bit. Okay, so we're on this Nerd server, and there's a couple tools, but we're just going to focus on on this FAME3 site, FAME3 for now. So which is just the location of phase 1 and phase 2 metabolism. So FAME3 right in the middle. Okay, so I'm going to just jump into, I'm just going to click the phase 1 metabolism link. So we're going to predict phase 1 drug metabolism, the location. Let's go back to my PowerPoint. Okay, so Decorramine, it's a tricyclic antidepressant that we talked about early in the course. Where would you potentially predict phase 1 metabolism? Anybody want to say? It's a very simple drug molecule. So what functional groups may get metabolized? It's designed to be a very easy example, right? I don't know. Remember, I mean, phase 1 metabolism is frequently oxidation of carbon and maybe oxidation of nitrogen. So I would probably say, this nitrogen could potentially be oxidized, but it's probably going to be this terminal one. And if it gets oxidized on the nitrogen, that can make nitron or something, nitrosamine type things. But also if it oxidizes on the carbon, like if it hydroxylates the carbon, then that can kick off and demethylate, right? So it's like a demethylation type thing. So that's my prediction. So let's take a look. Let's see if it works. All right, so I'm going to paste the smiles. Did I get the smiles? I don't have smiles yet. Let's get the smiles. Okay, I'm pasting the smiles of this Decorramine. And I'm going to submit it. Takes a second. Maybe 15 seconds. While it's going, yeah, I mean, the other nitrogen could potentially be metabolized, but the ones that are kind of hanging off on the periphery, I think, are a little more likely to react. Okay, it's coming, it's coming. Okay, it worked. All right, so molecule 1. So pretty much matches my prediction. And so probability score, I mean, it's from 0 to 1, and it's basically saying what we were suggesting, that probably it's going to be the terminal carbon or maybe the nitrogen. Both of those are likely to be metabolized. Okay, what the metabolite structures are is the other tool, the Glory tool. So we'll see how that works. Other things that might react are maybe N6, but that's pretty low probability. I think it's just so shielded by the rest of the molecule. So anyway, this is a nice little tool for probability of metabolism. Okay, given a structure. Okay, so that's that. Let's see what else. Oh yeah, that was a smile, so I was hiding from you, but it's on the PowerPoint. Xanax is one of these benzodiazepine sedatives. Any predictions on this, on the metabolism of this? This is a little different, right? Think back from our, this is where, I mean, if you have totally forgotten what we said about drug metabolism, then this is hard, right? Anybody remember something that could happen to this? It's different than the top one, because in the top one we have like a alkyl amine, and the amine can be oxidized or dealkylated. But there are reactions that can happen to this. Anybody remember those? Some of those metabolism reactions?
Can it be aromatic hydroxylation?
Perfect. That's exactly it. Yeah. Yeah. So that aromatic, the benzene here, can be oxidized. That's probably what my prediction. We'll see what that tool says. But yeah, and that's, you know, and you know, which benzene? Probably not this one, because it has the chlorine on it. The chlorine kind of blocks that, and you know, it blocks it sterically, and also it blocks it electronically, because it's the chlorine's pulling electron density onto it, and that makes the benzene less nucleophilic or electron rich. But this one's actually kind of exposed, and those kind of benzenes are susceptible to aromatic hydroxylation. So let's see what happens. Let's see if this server predicts that. So go to my PowerPoint, copy the smiles. Go back. Okay. We're going to predict phase 1 metabolism. Submit. And of course, this one, as it's going, if it did get para-hydroxylated, that would make it susceptible to maybe a phase 2 metabolism, like glucuronidation, or, you know, right? If the hydroxy group got installed, that's a nucleophile that could attach to sulfates or glucuronidation, etc. So that's often a cascade. First phase 1, then phase 2. Okay, let's see what's going on here. Okay, it says it worked. Let's see. C20. Okay, so C20 is one of the top ones, but it's not the top. It's not predicting it as the top reaction. I definitely think it would. I would expect para-hydroxylation to be a pretty dominant one, but it's, you know, above most of the structure. Yes, it is. It's actually kind of suggesting, and these are reasonable. The methyl group and this C16. Let's take a look at those. Oh, actually, yeah, that is actually pretty reasonable. That the methyl group that's kind of poking out is next to a heteroaromatic ring system. So that's actually pretty reasonably oxidized also, because it goes through a radical, and the radical would be resonance stabilized. And also this one is also next door to it. So yeah, these are all these two are definitely very reasonable metabolism sites. And also the para-hydroxylation, I think, it's ranking it a little lower than I kind of expect it to be. What's this fame score thing? I'm not actually 100% sure. We're probably gonna ignore this and just kind of focus on the probability, which makes sense. Okay, so okay, cool. All right, let's see. So yeah, this is a pretty cool tool for this phase 1 metabolism prediction. Okay, FAME 3 for phase 2 metabolism. This will just look for where phase 2 metabolism might occur, like where might conjugation occur, for example. We're going to go back to decypramine, and we're just going to focus on this unmetabolized drug and say, where might phase 2 metabolism occur? Prediction's probably going to be on the amine, right? That is a free nucleophilic atom, so that's you know, probably pretty reasonable to be metabolized. Oh yeah, I want to do phase 2 metabolism for this one. Okay, we switched to phase 2 metabolism. So our prediction is probably going to be attachment of a conjugate at the nitrogen. Another nice thing about this tool is you can feed in like 1,000 molecules and get 1,000 predictions. It's a free tool like that. And so this can be used, in a kind of a drug discovery platform, or like a drug discovery research project. Okay, it worked. And as predicted, it's predicting one phase 2 metabolism site exclusively, which is that secondary amine, with a very high probability, and nothing else even measurable. Of course, it makes sense that conjugates could not be attached elsewhere because there's no like nucleophilic free atoms, I guess, right? So that was nice. Okay, so ethanol is a beta blocker, beta adrenergic receptor antagonist. What do you guys think for phase 2 metabolism sites? Anybody? Attachment of conjugates. Probably the alcohol or the amine, right? Maybe that primary amide over there. Maybe the primary amide. It's a little less nucleophilic because it's in resonance and whatnot. But yeah, that's a reasonable prediction. Let's copy the smiles. We're still in phase 2. Smiles, paste, submit. Here and there, this website's complaining that I'm doing too many submissions and I have to wait like 10 seconds. It hasn't complained yet, but it's kind of annoying sometimes. Try refreshing. So again, my prediction is probably going to be the oxygen or the nitrogen. And high probability of the oxygen 19, the alcohol, makes sense. N18, what's that one? N18, it's actually saying the primary amide is a pretty reasonably metabolized position. I mean, it is nucleophilic. The NH2 there is nucleophilic there on 18. And then N4, which is over here. Maybe the reason N4 is not as predominant, my guess is that it is a little bit sterically hindered by the isopropyl group. I don't know. But yeah, alcohol, very high probability. Alcohols are very notorious for phase 2 metabolism. All right, cool. That was kind of fun. Let's see if we can actually predict metabolite structure, which is definitely another cool thing to do. We're going to try the Glory tool for this. Okay, so Decorramine. What type of phase? Oh yeah, what type of metabolism would we suggest? We already predicted the site of maybe the carbon and the nitrogen. So what might the products look like after phase 1 metabolism? What's it going to look like? I mean, you can oxidize the carbon to a hydroxy group, but that's not stable, right? So what happens if you oxidize the carbon to a hydroxy group, then the hydroxy kicks off and you make formaldehyde and basically you make an amine, right? So we're expecting dealkylation. I think that's a pretty reasonable prediction, right? And let's see if it makes that prediction. Okay, so I went back a couple links. Oh yeah, FAME3. It looks like they have 2 of these tools, and I didn't realize that. But I think they added one recently. I'm going to try the first tool, the first Glory. They also have something called Glory X because they are continuously updating these tools. So we'll try the Glory tool. So I'm going to paste the smiles of that molecule, and we'll submit it. So prediction is probably going to be dealkylation, maybe oxidation of the of this terminal or the tertiary amine. Tertiary amine maybe to the hydroxyl N oxide or something. Refresh. Okay, so the input molecule is the first one. And then, oh yeah, it's actually making some other predictions too. It's predicting aromatic hydroxylation, for example, on the benzenes. That's nice. It's predicting N-hydroxylation, which seems like a reasonable thing that can happen also. It's also predicting dealkylation, so the nitrogen being dealkylated. And that's again through what happens is that initially the methyl group gets oxidized to the hydroxy group, and then the hydroxy group kicks this off. Okay. And then what's this last one? This is a possibility. I think it's a little unlikely. What is, anybody know what that functional group's called? It's organic chemistry, organic 2, Chem 335. Carbon double bond nitrogen is called a, not an amine, but a, somebody said imide, I-M-I-D-E, and then somebody else said imine, I-M-I-N-E. It's only an imine, yeah. Yeah, this is an imine. It's one of the, it's basically the product of an amine and a ketone or aldehyde. But the thing about an imine is it's very unstable. So yes, it might form, but then it's going to get cleaved and basically make the amine again. So which is this one down here. So yes, possible, but likely to be destroyed then. Oh yeah, this thing, that's what I was talking about. That's like, that's also it's an intermediate structure, but it's going to be unstable. And then usually either the hydroxy group kicks in and then nitrogen kicks off, or the nitrogen kicks in and then the oxygen kicks off, and that's what it formed as the amine. Anyway, so yeah, it's nice to be able to see some of the possible metabolite structures. Only some of these are actually stable though. So, okay, let's see what else I got. Ethanol. Okay, so any predictions on what the metabolites might look like? Any predictions? I mean, I kind of think, I'm kind of anticipating similar type thing of maybe dealkylation. So, you know, this carbon is labile to oxidation, so it could maybe hydroxylate here, kick off the nitrogen, and that would make acetone. That would make a ketone, right? Potentially oxidation of the alcohol, maybe to a ketone, right? Oxidation of an alcohol is not that common, but it is one of the options. Yeah. Let's take a look. So I'm going to go back to Glory. And we're using the default settings. I'm curious about the other, Glory, the second Glory, Glory X. I haven't tried that one. I imagine for these simple molecules, it's not going to make a huge difference, but let's see, submit. No, it's not complaining good. I was worried it was going to complain that I'm using it too much. If you're doing it for homework, you may have to spread out your searches over a few minutes also. You will do something like this for homework, of like kind of predicting the probability and the metabolite structures. Okay, so it's ethanol. That's the input molecule. So, oh yeah, acetone. Like I was saying, that's a likely metabolite, and that was but basically from oxidation of the isopropyl group, and then the oxygen kicks in and kicks off the nitrogen, and that would create acetone, right? So then we have another possibility is just the hydroxylated amine, the right. Then, like we were saying, the intermediate with hydroxy group and the nitrogen. In the chat, does anybody remember what the name of this is? This functional group arrangement? If this was an oxygen, if what I have is a nitrogen was really an oxygen, it would be called a hemiacetal, right? Hemiacetal. But if it's an amine, it's not a hemiacetal, it's a hemiaminal. Almost like animal, but spelled differently. Okay, so yes, this would be a little different, and it would have the oh, I'm sorry. Yeah. So this is a likely intermediate, but it's unstable. Hemiaminal, right? But once this kicks in and kicks off, you would get the free amine, and that's probably what this is. No, it doesn't show it actually, huh? What it is showing though is potential hydroxylation of this position next to the benzene, which is actually possible too. Okay. So my only complaint here is that it doesn't actually show the degradation of the hemiaminal, which would give us the free amine, which I would totally expect as a byproduct. Okay. All right, cool. So that was a little bit on this Glory tool. That seemed to work pretty good. I'm going to try the Biotransformer tool. It was being a little funny. It's not part of NERD. It's part of this Canadian metabolite structure prediction thing. It is good for phase 2 metabolite structure prediction. NERD was not good for that. So if I'm trying to predict phase 2 metabolite structure, NERD wasn't doing that successfully. Because that's why I found this Biotransformer tool. Okay, so let's try it out. There's the link. It says that it's down, but it seems to sort of work still. So yes, I mean, I don't know. It seems to be okay still, but a little iffy. We'll see if I can get it to work at all. So I go to metabolism prediction right here, and I'm going to predict metabolism phase 2 transformation. Actually, let's try phase 1. I just want to see. I want to try the reaction we just did a second ago, the ethanol. I just want to see if that works. And if it does it any differently. I haven't tried this. This is experimentation. So, oh, whoops. So let's get the ethanol. Ethanol. Let me get that real quick. Okay, so I'm going to try ethanol, the beta blocker. Submit. We'll see how this compares to the NERD server. Yeah, 13 predicted metabolites. Oh yeah, how did I get in here? It shows this is like the result page, and I clicked this this Q579 thing, and then it showed me these. So these are all predicted metabolites. Let's see what they are now. Now to view I can just click these little arrows. Oh, that's actually kind of cool. So this is actually predicting the ketone oxidation, which I actually predicted myself. What's enzymes here? Oh, so this is really cool. So this actually may be a little cooler than the NERD server. it actually predicts which cytochrome P450 variants will cause this reaction to occur. So we could actually do this experiment, because I could go purchase these cytochrome P450s isoforms, 1A2 and 2C19, and actually try this experiment and then see if it actually happens. Terminal desaturation sounds like removal of a double bond. Let's see. Or desaturation. Yeah, desaturation. That's another word for oxidation. Yeah. So this nerd server said the same thing. Oxidation of the alpha position next to the amide. That's another set of cytochrome P450 isoforms. Let's see. This looks like, what's it doing? Oh, this is kind of cool. It looks like it's you know what it's doing here? Does anybody see what it's doing? It's doing an oxidation. It's a dealkylation, right? Let me see. Can I zoom in there a bit? How is this happening? What's the mechanism? This is a mechanism problem, right? So it's a P450 metabolism. So what's it doing? How is it ultimately cleaving the molecule into two pieces? It's probably hydroxylating right there, right? Is my yeah, you can see the mouse. It's probably hydroxylating right there, which makes a not aminal, but a hemiacetal. And then it's probably kicking off the hydroxy group to lead the phenol and the aldehyde. So that's actually a likely metabolism route also. That's cool. Epoxidation of a thiophene, let's see. Which is weird because I don't see a thiophene here. I don't know. Oh, this is just another aromatic hydroxylation. O-demethylation. This is the one I was talking about earlier. It says it looks like it's oxidation of the isopropyl group, and then kicking off of acetone, essentially. I don't know, these names are wrong, but the reactions look right. The reactions make sense, and I would predict this reaction also. Another dehydrogenation. This is probably just an oxidation somewhere. What did it do? So this is another interesting one. So what's it doing here? It's predicting oxidation of the methyl group, which is actually not very favorable, right? The more likely oxidations are right next to the nitrogen, or right next to this oxygen, or right next to this oxygen. So this is possible, but I'd say kind of a low probability. Does anybody remember why is it favorable to oxidize like next to nitrogen, or next to oxygen, or next to oxygen here? Anybody remember? Something about it makes a radical, and the radical is a little stable. So the radicals are actually stabilized by the neighboring nitrogen, neighboring oxygen, neighboring oxygen. This is not a very stable position. So this is possible, but not very probable. And I actually did show some of these kind of weird random oxidations and that are like known in the literature. But anyway, so I think this is a kind of maybe a little less likely. What about this one? Okay, it looks like, yeah, this is we'll go back to functional group identification. This is not an imine. It's called it's like an imine. Same chapter as the imine chapter in your organic book. It's not an imine. It looks like an alkene with an amine. It's a enamine, right? This is an enamine. And so this is also just a result of hydroxylation of the isopropyl group, and then it kind of kicks off water, and that would give you this enamine. So enamines are another possibility. Okay, let's see, epoxidation of arene. So this is probably just going to be another aryl hydroxylation. Yeah, you know, that is actually possible. It's probably going to degrade then, and I don't know. It's a prediction. there's not, I mean, and it's nice that computers are able to do this prediction, but to really validate this, you'd have to do the experiment. Okay, well, anything else? Anything else? Another, this is, yeah, this basically what we were talking about all along. Hydroxylation of the isopropyl, kick in, kick off, and then you're left with the amine. All right, good. So this is probably, to me, the most likely metabolism. Okay, so let's try the phase 2 one. Let's try the phase 2 one. I tried phase 1. Let's try phase 2. Okay, let's see if it can predict some phase 2 metabolism. Okay, so we're going to let's see here. Sorry. So we're on this Biotransformer tool. Blah blah blah. Okay, so let's predict the phase 2 metabolism. Let's see if it works. I'm not sure if it'll work. We'll see. So remember tamoxifen? It's the breast cancer drug. It's an estrogen receptor antagonist. And how this tamoxifen was not an active drug, but P450 would oxidize it at the para position, so aromatic hydroxylation. And then this was the active drug, actually, right? So it was a prodrug, right? So let's see if we're going to predict phase 2 metabolism of the hydroxy group. Does anybody have any predictions of what phase 2 metabolism might happen on this hydroxy group? What were the phase 2 things of a nucleophilic atom like hydroxy? So they all had kind of funny names. One was glucuronic acid. It was like a sugar with an acid, and that would make an ester. Other ones were like sulfate. So sulfate can get conjugated. Potentially an amino acid like glycine or glutamic acid could be attached also. But let's see if the Biotransformer tool makes a prediction about this. Any predictions? So we have a couple predictions, probably based on the hydroxy group, right? No other site here would be a phase 2 metabolism site. It's really going to be the hydroxy group. So there's 4-hydroxy tamoxifen. Okay, so I went back. We're going to try the phase 2 transformation link. It's metabolism prediction, phase 2 transformation. Let's see if it works. I'm not too sure if it will. We'll try it. That's a bit. So what kind of phase 2 metabolism will we get on that hydroxy group? Okay, so it did something. Okay, it's a number of predicted metabolites 0. So I think it didn't work. The website's been a little funky lately. I think I may have one more thing to try, and that might work. So anyway, probably gonna skip this one. But our predictions are probably sulfate or glucuronic acid, right? That's reasonable. If I give you homework ones, I'll make sure they work. But right now the website's a little funky right now. Okay, let's try another one. I think I have another one. Fusidic acid is an antibiotic, steroid-looking thing. What kind of metabolism might you expect on this? Well, probably the same kind of things, right? You have alcohols, these secondary alcohols, maybe something on the carboxylic acid, maybe amino acid could get conjugated. You know, those are kind of the predictions that we might make. So let's see if this works. Again, this is cool that we can paste this SMILES string, which is the full chemical structure of this molecule. Let me see if I can do that. Okay. Phase 2 transformation, paste, submit. So it actually did predict one, at least one molecule. Let's see what it is. So it did kind of anticipate maybe a sulfonation of that secondary alcohol there as a potential metabolite. You know, I could imagine also glucuronidation, maybe something onto the carboxylic acid as well. But yeah, it did make a little bit of a prediction, which is nice. All right. And you know, why maybe not the other hydroxy group? What's special about this hydroxy group? Might be a little more sterically available. This one's a little, you know, it's directly next to this methyl group and also this other ring system. This might be a little more open over here out on the left, although it's also next to a methyl group. Okay, anyway, so that's that. Maybe glycine or glutamine conjugation to the carboxylic acid. Okay, so I guess we're almost out of time. What I'll do is I'll, in the asynchronous lecture, I'm going to talk a little bit about these things. I may actually skip that because I want to be able to talk to you guys about this. It might be better to do this part as Zoom. I may change my mind. I'll look at this stuff, and if I decide it's easier to do by Zoom, I'll just do by Zoom. Otherwise, I'll post a second video like I've been doing. All right. But we're getting into some kind of cool things, and not really. It's hard for me to really demonstrate this in a way that you could do it, but I can definitely talk about it. The concept of virtual screening, in silico synthesis, which is, oh yeah, you'll do that. Yeah, in silico synthesis we will be able to do. What does that mean again? That means doing synthesis on the computer, which is really cool. And that is something that you will be able to do, and you'll be doing in a homework assignment. Homology modeling, docking, and molecular dynamics. These things are also, I can demonstrate them, but I can't really, not to the extent that I can have you guys easily do them. You might do this in a computational course. But the in silico synthesis is definitely something you guys can do, and you will do. It'll be fun. And then I'll do a couple of these case studies. All right. So I'm probably going to skip the asynchronous lecture this week, just because it's going to be much easier to do this in person with you guys next week. Especially the in silico synthesis, which is a little complicated. It's got to be kind of a dynamic, you know, thing where I'm talking to you. All right. So I think we're good. Are we good? Any questions about this? Okay, I think we're good. All right. Well, have a wonderful night, and happy Veterans Day. No class tomorrow for, well, not with me anyway, but there's no class at all tomorrow. And I will see you guys next week. I may have a homework assignment ready for just some of the metabolism details we've been doing that I post on Friday, and then you'd have a week to do it. All right. All right. See you guys. Bye-bye.